Okay, now we look at the example 7. So you are given a complete set of double integral where you are given the order is dy dx as constant with their limits. Okay, so maybe you just want to directly integrate. So see what happened. So when you integrate, okay, you have the ay squared dy, which means that you have a layer of function. Okay, so I mean there is a y squared in the exponential function. So in that case, you have to use the substitution. So you let u equal to y squared. So why we need the substitution? Because we want to make sure that the expression that we have so far becomes more simpler. But normally, if you see that it's become complicated, then you have to stop. Okay, now we want to see it. So for me, because I always seen this I see this many times, so I can expect I cannot directly use the order given. Okay, I have to reverse the order because it is complicated to be. I mean, I can if you directly integrate, it becomes harder. So I have to reverse the order. But maybe for you, you have no idea. Then we can just directly integrate. So see what happens. So you let u equal to y squared. So you want to have the dy. So you have to differentiate. So du over dy will give you 2y. So by hoping that after you apply the substitution, so your expression here becomes simpler, then you can directly integrate with respect to y. Okay. So now when you substitute into your inner integration, so you have u, and then you substitute. So now your dy is become du over 2y. So you have du over 2y. So now you have u over y du. So the aim is when you are applying the substitution, you want to change all the y terms into u. But now you can see this one's supposed to be u. So now you can see your y still there. And then maybe you can say, okay, I can replace the y using this equation, which means that now you have y equal to plus minus square root u. Okay, so now you have eu, and then plus minus square root u du. So now everything is in terms of u. Yes, that is correct. You managed to transform everything from y into u. But then see your expression now. It becomes simpler or becomes complicated. Now you have to integrate this. So this is not something not easy to be done, right? So meaning that you cannot directly proceed using the given order. So you have to reverse the order. So just like previous example, now we have to reverse the order, which means that you have to find the new limit of x, the new limit of y, where y now is a constant. But then you are not given the region. So we need the region to help us in determine the limit of the x and the y. Okay, so now how can we get the region? So we can get that from the existing limit that we have. So the existing limit, we have x from 0 to 4 and y from x over 2 to 2. So from here you can have 4 equations, which means that you have x equal to 4, x equal to 0, y equal to 2, and y equal to x over 2. Okay, so now we sketch the line. So we got 4 equations again. You have among these equations, so this is will give you the exact the shape of the region, or the shape of the region. So you have the linear equation pass through the origin. Okay, so now you have the line x equal to 4. So this is y and this is x. So you have the line x equal to 4, x equal to 0, you have y equal to x over 2, and you have y equal to 2. So where is y equal to 2? So now we want to know what is the intersection point here. So when x is 4, okay, because this is the intersection between the x equal to 4 and y equal to x over 2. So when x is 4, so y is 2. So meaning that the line of y equal to 2 is here. Sorry, that is the line. Okay, again, so which is which? Which one to be your region? Yeah, I know that you can read from this limits, but still confusing. So again, back to your order given. So your order given is dy dx, x constant. So you must have the vertical line, right? So vertical line. This vertical line will help you to determine the correct region. Okay, and it also help you to determine the correct limit. Okay, now based on the limit given, we want to shade the area. Which one to be your region? So now you read from your interval, the given interval. So you can see that the line here is between x equal to 0 and x equal to 4. Now you read for the y. Who is your first point? Your first point is at y equal to 2. So where is y equal to 2? So, okay, it's constant. So where is y equal to 2? Sorry, so it should be, this is your initial. So initial is x over 2. Where is the line of y equal to x over 2? So this one, this is the first. And the terminal is y equal to 2. This one. So now here you know that your region is this area. So that is your region. So from the region that you have sketched, now we want to proceed with the new order, which means that y now is constant. So you have to provide the horizontal line. So now y is constant. So y is lying between 0 and 2. And how about x? So when you are here, you move along the x-axis from the left to the right. So from the left, so your region is and at this area. So we can see that this is your initial point and this is your terminal point along the horizontal line, which passing through through the region. So your initial point here is x. Now we are read for x. Okay, x equal to 0. And this one belongs to the line of y equal to x over 2. But we want x equal to. So x equal to becomes to y. So that is your new limit. So now we substitute. So y is 0 to 2. And then your x is 0 to y. Okay, and then we proceed to integrate. Okay, so you want to integrate first with respect to x, but these are all in terms of y, so y squared is constant. So then we can just take this out because this is constant. So we just look at the integration of 1 dx and then dy. Okay, and x from 0 to y, y 0 to 2. So now we settle down for the first integration. So 1 dx will give you x, and then the limit of x 0 to y dy. So now replaced. So 2y minus 0. So now you can see that everything is now in terms of y. If you still see the x, so you do something wrong. You did something wrong and you have to double check. So now you have 2 is Okay, now your new form, I'll put the 2y in front here, 2y y squared dy. So you can see that you have y squared and you have 2y here. It looks like when you do, you have no the most appropriate method of integration here is substitution. So now you can see that when you do the substitution, you will get the 2y, right? You have to let u equal to y squared, and when you differentiate that, you must have the 2y, and then using that 2y you can get from your substitution, and you have the 2y here, so they are gone. They will gone. So when then your expression becomes simpler. So hopefully you can see that. What I mean is, now we have to use the substitution. So let u equal to y squared. So you have to differentiate with respect to y, and then you have dy equal to du over 2y. So now when you substitute all your assumption, so you have 2y u, and your dy is du over 2y. So your 2y here can be cancelled out. So in this case, the substitution works. Okay, but if you do the substitution from the beginning, it doesn't work because it becomes complicated. Okay, because you can see the eu over u is, and square root u, in fact, and you cannot solve that one easier. But in this case, even though you apply the substitution again, but then because of you settle down for x first, and you manage to simplify your integral, just becomes eu du. So now we integrate eu, we'll give you eu, and then you have to substitute the limit y is 0 to 1. 0 to 2. But that one is the for y. But we have u. Then you have to replace back what is your u. So e y squared y 0 to y equal to 2. So now e 4 minus e 0. So e 4 minus 1.